All right, welcome back, Algebra 1. Today we are doing our sort of last lesson over quadratics before we start rearing up for our state test and prepping for that mainly. So we're going to look at this warm-up. So a bottle rocket's height is modeled by the quadratic h of x equals negative 2x squared plus 14x, where h is the height in feet after x seconds. How could we try and find when the rocket was 20 feet high? So what are a couple strategies that we can do in order to calculate this? When is this quadratic going to be 20 feet high? Or when is the rocket going to be 20 feet high? Well, if we think about it, height from this question, 20 feet high, that represents height. We were told that the rocket's height is modeled by the quadratic. So we're just looking, when is this quadratic equal to 20 feet? So when is this quadratic equal to 20 feet? So there's a couple ways we could solve this. We could, if we get this equal to 0, we could use quadratic formula. That we've been working with plenty of times. We could potentially factor. I don't know if this factors, but it might. We could graph it and look, when does this quadratic equal 20? Or if we graph each of these two separately, as what we could see when this quadratic equals 20 on the graph. So there's a couple things to think about. So what do we call it when we have multiple equations and try to find when those equations are equal? So for example, if I had y equals 2x plus 3 and y equals negative 4x plus 8. So these were known as systems of equations. Now, in the past, when we did systems of equations, we only used linear equations. So we did systems of linear equations. Well, we're going to expand that today, and we're going to throw our quadratics into this. So we're going to try to do systems of equations involving quadratics today. So when can we use these quadratics? When are they equal to certain equations or certain lines? And we'll see that. Now, what do you think are some differences between linear systems versus linear quadratic systems? So what are some differences? Well, when we are doing linear systems, we always got a single value from when those two lines were equal. So we always had a single coordinate point that was our answer. It was an x and a y. So that was our answer for a linear system. Now, with quadratic systems, so when we do a linear and a quadratic line, so you have a line, let's say like this line right here, and then you have a quadratic like this. That quadratic is crossing that line or intersecting that line at two different locations. So we're going to get two answers. You're going to get two values of an x and a y for these problems. So not only are we going to get one solution, but we're going to get two solutions with these. And we're pretty familiar with that whenever we deal with quadratics, getting two solutions. So it's important for us to remember that it's possible for us to get one solution. Maybe it's possible for us to get two solutions. Maybe it's possible for us only to get one solution from a quadratic. Or, it's also possible that the quadratic completely passes over the line and we have no solutions. There's nothing there. And so we need to be careful when we solve these linear systems, linear quadratic systems, to remember that we're going to get all those different possibilities for those answers. So let's start with that warm up again. So we model a quadratic, or a model rocket is modeled by its height is modeled by the quadratic h of x equals negative 2x squared plus 14x, where h is the height of the rocket after x, or in feet after x seconds. How could we try to find when the rocket was 20 feet high? So once again, we essentially have the equation y equals negative 2x squared plus 14x, and then we have the second equation, y equals 20. So we're looking for when are these two equations equal to each other. We kind of set it up earlier already in the problem. We know because they're both equal to y, and we're looking for when they're equal to each other, we can set them equal to each other. So I can do negative 2x squared plus 14x equals, because it's equal to the same thing, we're sitting when they're equal to each other. And this is super easy. In order to solve this, all I need to do is, I know I just have to get my quadratic equal to 0 on one side, and then I can go from there. So if I minus 20, I have no constant number over here, so I'm just going to minus 20 and put it at the end. So I'll have negative 2x squared plus 14x minus 20 equals 0. And then we can solve this in order to find when our rocket is going to have that, and we're going to get those answers. Now, I'm going to solve this using quadratic formula, so I need to first put down my a I got to put my A, my B, and my C. So my A is -2, my B is 14, and my C is -20. Remember, I just need the numbers. I do not care about the variables necessarily, but I do care about the sides. So think about it, my quadratic formula is opposite of B plus or minus square root B squared minus 4AC all over 2A. So we can start filling in our information for that quadratic formula. So we have opposite of B, so it's going to be -14 plus or minus the square root of B squared, which is 14 squared, minus 4 times A, which is -2, times C, which is -20, all divided by 2A, which is -2. From here, I can simplify and start rounding my pieces together. If you want to, you can put this whole thing into a calculator if you wanted, if you feel comfortable typing it all in, as long as you put a plus or a minus, or put plus for one time and then plus for a minus to make sure you get both solutions. I'm going to start with 14 squared, though, because I know I need to start under my quadratic, or under my square root, I'm sorry. So 14 squared is 196, minus 4 times 2 times 20. Well, -4 times -2 is +8, times -20 is going to give me a -160, all over 2 times -2, which is -4. Sorry about the bell. All right, -4, or so if we do 196 minus 160, that's going to give us -14 plus or minus the square root of +36 over -4. So we already know we're going to get not thinking about yesterday. We're not going to have a complex solution because I see that the number under my square root is a positive number. So I know I'm going to have a positive solution. So there will be real answers to this, not complex answers. So whenever we're dealing with real life situation problems, we should always get real solutions. If you're getting complex answers for real life situation problems, then probably somewhere along the quadratic you messed up. So let's see, radical 36. Radical 36 actually is a perfect square. So that's going to give me just 6. So this is -14 plus or minus 6 over -4. Well, I know once I get to that plus or minus part, I can split into 2 different problems. And because I don't have a radical anymore, I can actually find the actual solution. So -14 plus 6 over -4, and -14 minus 6 over 4. So -14 plus 6 is going to give me -8, divided by -4 is going to equal x equals +2. My second point is -14 minus 6 is going to give me -20, divided by -4 is going to give me +5. So x equals 5. Now, once again, we said our solution should be 2 actual coordinate points. So it's going to be 2 coordinate points. So the 2 coordinate points that I have for my solution, if I got 2 and 5, we know this is when our quadratic's height was equal to 20. So the rocket hits the height at 220, and the other coordinate point that they intersect is 520. So we knew that the x represented the number of seconds. So after 2 seconds, the rocket's going to be 20 feet up in the air. And after 5 seconds, when it comes back down, it's going to be at 20 feet in the air. So if we were to draw a picture with our quadratic, our rocket's going to fly up. And at 2 seconds, it's going to be at 20 feet high. And then at 5 seconds, it's going to be at 20 feet high. So those are the 2 coordinate points that we found for our quadratic. Let's do another example of that. All right. So a Stokes value is modeled by the equation f of x equals 2x squared minus 14x plus 30. Another Stokes is modeled by the equation f of x equals 5x minus 5. At what point will these Stokes be the same value? And what is that value? So we're looking for when are these Stokes going to be equal to each other? Well, we know whenever we're looking for when these Stokes are going to be equal to each other, we can just set those equations equal to each other. So 5x minus 5 is going to be equal to 2x squared minus 14x plus 30. I'm just setting them equal to each other. And I know all I have to do is get everything to one side and then just solve. So I'm going to minus my 5x, which is going to have to subtract from 5x over here. So that's going to turn into negative 19x. If I add this 5, I'll add this 5 over here because it has to go with my positive number. So that's going to turn into positive 35. And then it's going to be 2x squared is going to be the same as well. So I inversed both of those values to be able to get 2x squared minus 19x plus 35. And from here, once again, we know how to solve this. All we have to do is I mean, you could try to factor, or you could graph. I'm going to do quadratic formula, though, because I think that's easiest. So A is 2, B is negative 19, and C is 35. So plugging all this information into my quadratic formula, I have, let's see, opposite of B plus or minus square root B squared minus 4AC, not C, 35, sorry, C all over 2A. So plugging this in, if I know I always need to start under my square root, so I have 19 plus or minus the square root of negative 19 squared is 361. Negative 4 times 2 times 35 is going to give me 280, negative 280, all over 4. Well, I know I can simplify this. Negative 61 minus, or sorry, 361 minus 280 is going to give me a positive 81 over 4. So 19 plus or minus radical 81 over 4. I know the square root of 81 is just 9, so I have 19 plus or minus 9 over 4. And I know I can split these into two problems. So I have 19 plus 9 over 4 and 19 minus 9 over 4. Sorry if you can hear that once again. 19 plus 9 turns into 28 over 4, which is going to give me x equals 7 as one solution. 19 minus 9 is going to be 10 over 4, which is going to give me x equals 2.5 as my second solution. So at 7 and 2.5, whether these, it doesn't specify what the time length is this, or it says when they, or at what points would these stocks be the same value. So we know when x is, what was it, 7, and x equals 2.5 are when they're going to be the same value. But what is that value going to be? What is that value? So what is the y value? What is the output when x is 7 and x is 2.5? So we have to find both these coordinate points. So I have my x's. Now, just like with our linear systems, we have to plug back in to find our y's. Now, I can choose either of these two equations to plug into, but I know, just like you, you're pretty lazy, I'm pretty lazy, I'm going to choose the easier equation. I'm going to choose my linear equation because that one looks much easier to plug back into compared to my quadratic equation. So I'm going to do this twice. I'm going to have f of 7. I'm going to plug that into my function. So I have 5 times 7 minus 5, which 5 times 7 is 35, minus 5 is going to give me 30. So my first coordinate is going to be 7, 30. That is one point on which my quadratic will be equal to this line. And I'm also going to do the same for my other point. So f of 2.5. I'm going to plug 2.5 into my function. So that would be 5 times 2.5 minus 5. Well, 5 times 2.5 is, what is that? 12.5 minus 5, which is going to equal 7.5. So my 2 points are 7 and 30, and 2.5, 7.5. Those are my 2 points on which my two stocks will be equivalent, and my two answers. And that's our linear quadratic system. So once we solve the quadratic, once you get x, remember we need to plug it back into one of those two equations. The easier one is always give me the linear one. So plug it back into that, and then you will have your final solution. All right, when do these equations intersect? Once again, we know how to set them up. All you have to do is set them equal to each other. This first one's very simple. We have x squared minus 5x plus 7 equals 2x plus 1. Once again, all equal to each other. So inverse at 2x, inverse at 2x, inverse at 1, inverse at 1. We get x squared minus 7x, because negative 5x minus 2x is negative 7x. And then positive 7 minus 1 is going to give me positive 6 equals 0. Honestly, this equation actually seems easy enough that I could probably factor it. But I think two numbers that multiply to give me positive 6 add to give me negative 7. If I think about my box and diamond method, I could probably factor this one pretty easily because I have 6x squared in my numerator, negative 7 x. So negative 1x and negative 6x multiply to give me positive 6x squared, and then add to give me negative 7x squared. So I can do those. So I'll have x squared, and then I'll have positive 6 I'll have negative 1x here and then negative 6x here. I can fill these in pretty easily. X times x times negative 6, x times negative 1. So my factors are x minus 1 and x minus 6 equals 0. I can solve each of these easily. I know whenever I factor and I have to solve, I can just set each of those factors equal to 0. So x minus 1 equals 0. X minus 6 equals 0. Add 1, add 1. That gives me x equals 1 is one solution. Plus 6, x equals 6 is my other solution. Now, once again, once I solve each of those, I have to set each of those, I have to plug those problems back into one of my two equations in order to get the y value, because I'm looking for the x and the y. I'm going to plug it into 2x plus 1. So I'm going to have y equals, let me do a different color so I'm not, let's see, y equals times 1 plus 1. Well, 2 times 1 is 2, plus 1 is 3. So y equals 3. So that coordinate is going to be, one of my answers is going to be 1, 3 is one point in where those quadratics are equal to each other. The other point that I do is going to be y equals 2 times 6 plus 1. 2 times 6 is 12, plus 1 is going to give me a 13. So my other coordinate is 6, 13 as my other solution. So those are our two values. Those are two answers of when those two lines will be equal to each other. It'll be at 1, 3 and 6, 13. So once again, we could solve these quadratics in any method that we enjoy, quadratic formula, factoring, whatever. Just remember that not every answer of a quadratic is always factorable. So sometimes you might need to use a quadratic formula. Sometimes you might need it, or sometimes it might be easier to factor. Sometimes it might not. So always keep an eye out for that. What about this one? So this is a standard form equation. It's in that ax plus by equals c form. It's x plus y equals 12. Well, in order to set this equal to my quadratic, all I need to do is think about substitution. I know my quadratic is y equals 5x squared minus 2x plus 8. Well, I have a y right here. Just like what we did with linear systems, I can substitute this entire quadratic. I can substitute this entire quadratic in for y because I know my entire quadratic equals y. So I would have, if I rewrote this top quadratic, it would be x plus, I'm substituting this entire thing, 5x squared minus 20x plus 8 equals 12. I'm just substituting this entire quadratic into that function in for y. So I know it's a lot of things to write in just for one variable, but we know our quadratic is equal to y, so it's perfectly okay. And then from here, I know I don't really have any number outside these parentheses, so I don't actually need those parentheses. So if I have x plus, this x is going to add into my negative 20 right here. So it's going to give me 5x squared minus 19x plus 8 equals 12. And then I know I can subtract 12 to get this all equal to 0. So I'll have 5x squared minus 19x minus 4 equals 0. And I could solve this using my quadratic formula. I might be able to factor it. You might come up with something for that. But we can solve that, and then we'll have those two values. Once again, once you get those two values, plug them back into the equation. I would plug them into the linear equation because that's always going to be easier. Solve for the y value, and then you have your answer. So that is all we have to do with linear quadratic systems. We could even solve these if you had two quadratics. Say, for example, you had the quadratic 2x squared minus 3x plus 4, and you're seeing when is this quadratic equal to 8x squared minus 5x minus 3. Once again, all we have to do is set these equal to 0, so get all the quadratics over to one side. So it just means you have to move a lot of things. So I'd have to subtract the 2x squared, subtract the 2x squared. I would have to add the 3x, and then subtract the 4, and subtract the 4 to cancel out this entire side. And I would be left with 0 would be equal to 8x squared minus 2x is 6x squared. Negative 5x plus 3x would be negative 2x squared, or negative 2x, and then negative 3 minus 4 is negative 7. And then you just have to see when is that quadratic equal to 0. You'll get your x, you get your two x's, assuming it has two answers. Plug them back in. You would have to choose either of those two equations to plug it into, which are both quadratics, so it's a little bit more work on that one. But once you plug it in, once you get those two solutions, you have your answer and you are done. So we can even do linear or quadratic systems where it's just quadratics. That's where we're going to end it for today. Let me know if you have any questions. You'll have some practice over this. Have a great rest of your day.